students, welcome to this lecture on preliminaries for the ODE course. Now in this lecture we are going to talk about something called a Lipschitz continuity. Okay, now what is that? So essentially what we have is this. Let's say that if you have a function f from ab to r, right? So it is defined on a closed interval ab and the range is in r. Okay, so real valued function, and you are assuming that you are starting with a point x0, right? x0 which is in open ab. So basically x0 is any point, so you have a, you have b, and x0 is the interior point of open ab, right? Okay, so we say that f is continuous at the point x0. Okay, let me just put it x0. If you let's say if you give an epsilon, you will have a delta depending on epsilon, right? Such that f of x minus f of x0 less than epsilon for all x minus x0 less than delta. So please remember this delta depends on epsilon and of course the point x0. Right, and also we know that I mean if this dependence is independent, so basically if this delta is independent of x0, so if this holds for any x0 in AB, let's say, then f is uniformly continuous, right? Uniformly continuous. So basically it does not really depend on any delta, x0. Uniformly continuous in AB, right? In AB. This is what we know from our real analysis. So essentially what I am trying to say is this. See, for a point x0, if you are given an epsilon, you have to find a delta which depends of course on the epsilon and the point x0 such that this happens. So basically you will have that fx minus fx0 can be made less than epsilon for all x minus x0 less than delta. This is what you need to do to show that this is continuous. And of course if this for any epsilon greater than 0, if you can find a delta which is independent of x0, then we say it is uniformly continuous in the whole interval AB. So basically it is independent of any such point, right? Now what are the examples? Examples we already know that let's say fx is x square, all those functions, right? X square. So any polynomials essentially, x power n. Let me just put it this way: x power n, n is in n. Let's say. So any polynomial. So this is continuous in R, right? Continuous in R. Doesn't really matter what you are going to take in whatever interval it is R. And also you can have fx equals to exponential of x, right? So that is also continuous in R. And similarly, you know that there are other examples which you can construct in the, right? So, I mean, there are lots of examples which you can construct in R. Okay, so that is continuity. But the thing is, what is missing from continuity is this. See, here it is saying that if you are choosing x in a small neighborhood of x0, your x also will lie in a small neighborhood of fx0, right? That's what it is saying. But the thing is, it does not give you a control on the growth of f. So basically what we want is we need to know how fast f is growing. It's not like exactly how fast f is growing, because that will give you differentiability. We need to know we need to put some kind of control on f, and that actually gives us a lot of information on f. Okay, so that is where the concept of Lipschitz continuity comes in. So let me just define what is Lipschitz continuity. Lipschitz continuity. Okay, so what you have is this. See, this concept of continuity depends on a point x0, right? So this is kind of a local concept. What I mean by local concept is depends on points, right? Or in a small neighborhood of that point. That is what we are looking at. Okay, of course if it is uniformly continuous, then it is a kind of non-local or global, you can say non-local. Non-local means it does not depend at one particular point but over the whole interval, right? So a similar sort of concept is Lipschitz continuity. What is Lipschitz continuity? So if I am defining from AB, right, AB to R, and we say this is Lipschitz continuous. This is Lipschitz continuous. Okay, continuous in AB, right? In AB, you see, Lipschitz continuity, we will not define it at one point. This is a non-local concept. Please understand, this is non-local. Okay, non-local. So what do I mean by this? I mean that it does not depend at one single point. So f is Lipschitz continuous in an interval AB if, okay, there exists m. Okay, m of course depends on the interval AB. Okay, so m depends on AB. Okay, but does not depend on any point. So m greater than 0 such that, okay, so there is a real number m such that whatever fx minus fy you choose, does not matter what xy you choose, you can always make it less than equal m times x minus y, right? So what I mean by this is, you see, you can of course control the growth of f, how fast f is growing, using the information that, see, we already know how fast x is growing, right? The range, the domain, how fast we are changing the point. So we are actually controlling that change in your x, okay? So the the domain. Based on that, we are changing. I mean, I am saying that we are changing the growth of f. We are controlling the growth of f based on the growth of x, right? That's what you are saying here. And this m, of course, this m, you can see that this m is independent of ab. Okay, so this should hold for all xy in ab. Doesn't really matter what xy you are choosing. This is there. So that is Lipschitz continuity. I hope this is okay. So what we have is, it is Lipschitz continuous over the whole interval AB. Please understand, this is not a local concept. This is a non-local concept. It depends on whatever the interval is defined, right? If you have a m greater than 0, again, if you have a uniform bound m, right? This is a uniform bound. And this m should work for all xy in R. So basically, this m will help you to actually control f in the whole interval. Is this clear? Okay, right. Now let's just understand what is so special about Lipschitz continuity. So with some examples, okay, examples. Okay, so f of x equals to, let's say, what is the first example that comes to mind? Okay, fx equals to x. So in R, let's say, in R, right? So let's see if it is Lipschitz continuous or not. Of course, you can see that this is going to be trivially Lipschitz continuous, right? So fx minus fy is equals to x minus y, right? So this is, again, you can actually write it. So basically, you see, I have to find a m such that, so I have to write it like this, less than equal m times x minus y, right, for Lipschitz continuity. But you can see that if we choose m to be 1, then this is Lipschitz continuous. So this m, so here, this m is called the Lipschitz constant. So here, this is also, this m, we will call it as a Lipschitz constant. Okay, Lipschitz constant. So essentially, you see here, for fx equals to x in R over whole interval R, doesn't really matter any bounded interval or in whole R, m equals to 1 is a Lipschitz constant. So this is a Lipschitz continuous function. Okay, let's look at some other example. Let's say fx equals to mod x. Okay, in R. Now we know that this function is continuous, right? So f is continuous, right? This we know, it is continuous in R. And of course, we also know that f is not differentiable in R, right? It is not differentiable at the point x, at x equals to 0, right? But the thing is it Lipschitz continuous? Let's just see that. Okay, so what we have is this. See, x can be written as x minus y plus y, right? This we can do. This holds for all xy in R. We can write it for any xy in R. This is, we can write, since then you see mod x is always less than mod x minus y plus y, equals to, yeah, okay. So I can take the modulus on both sides. This is the modulus function, right? So you see, then mod x can be written as mod of less than equal mod of x plus y plus mod y, right? So this is triangle inequality. Of course, triangle inequality holds in R, triangle inequality, okay. And then you can of course write that mod x minus mod y is less than equal mod of x minus y, right? So you see, and since x and y, see, it doesn't really matter if you are writing x and y. If you replace x and y with y and x, then you also have, so by symmetry basically, you also have mod y minus mod x is less than equal mod of y minus x, right? And since mod of x minus y and mod of x minus y minus x are basically the same thing, so these are basically same, right? Therefore, you can write that mod of mod y minus mod x, if you are putting the modulus function, this is always less than equal mod of x minus y. Okay, so what does that give you? You see, that gives you that f of y minus f of x, okay, this is always less than equal 1 times y minus x or x minus y, doesn't really matter, okay. So this holds for all xy in R, So you see, this function, this actually shares that this is your m, right? This is your m. So 1 is a Lipschitz continuous, fx equals to mod x is Lipschitz continuous over the whole interval R. Okay, and by the way, please remember this inequality, it is very, very important. So basically it says that mod of x minus mod of y So this is less than equal mod of x minus y. Okay, this holds for all x, y in R. Right, this inequality we are going to use it in many other places, but you do realize that you can use this inequality to show that therefore fx equals to mod x is Lipschitz continuous. Okay, Lipschitz continuous where? Lipschitz continuous in R. Okay. Now you have to understand why I am saying in R. Please, whenever you do Lipschitz continuity, make sure that you know where it is Lipschitz continuous, right? So for example, let's just put this example. Okay, see. Okay, let's say fx equals to x square. Let's just see if it is Lipschitz continuous in R or not. Okay, in R or not. Okay, so you have fx minus fy, and you can see that this is equals to x square minus y square, right? Y square. So that will give you x plus y times x minus y. Okay, now if you, let's say if it is Lipschitz continuous, if you are assuming it is Lipschitz continuous, this is always less than equal m times x minus y, right? Okay, so that will actually imply that if this is Lipschitz continuous, so let me put it this way, if f is Lipschitz in R, then there must exist m such that, okay, mod x plus y is less than equals to m for all x, y in R. Okay, but you do realize that this is of course not possible, because I can choose x and y sufficiently big such that this is not true. Okay, this is not true. Hence, if x equals to x square is not Lipschitz continuous in R, right? Lipschitz continuous in R. Okay, but you see here the problem is this: x, y, I am choosing it from R, right? And R is unbounded. So essentially, that is the problem, that we cannot bound it with a uniform constant, right? But if you are choosing f from a bounded set, so basically let's say fx equals to x square in a bounded set, let's say in closed bounded set AB. Let's just choose it like this. Doesn't need to have to be closed, but let's just choose it like this. Okay. So in that case, you see fx minus fy can be written as less than equal. So basically you can write it as mod x minus y times mod x plus y. This you can do. And then you see this is less than equal m times mod x minus y. Okay. Of course, in a bounded set, so basically what is your m here? M is equals to 2b. Okay. So basically let me write it this way. See, let me do it properly. You see here, since mod x plus y is always less than equal mod x plus mod y, this is triangle inequality, right? Triangle inequality. Hence you see this is less than equal, and mod x is always bounded by b, right? So this is always bounded by 2b. So this is 2b times mod x minus y. Okay, so this is your m. So therefore fx equals to x square is Lipschitz continuous in closed AB with what is the Lipschitz constant? So with Lipschitz constant. Okay, what is the Lipschitz constant? 2b, right? Okay, so I hope this is clear to you, that whether it is Lipschitz continuous or not. Okay, so you have to check one problem now. So check fx equals to x log x, let's say log x is Lipschitz. So basically the question is this: can you find a function, can you find a domain Lipschitz in I? Okay, let's say if I put it diagonally, does there exist such a y? Does there exists such an I? Clear? So basically what I am trying to say is this: does there exist an interval I where fx equals. Now once we have that Lipschitzness, the concept of Lipschitzness clear, there is another concept which is called locally Lipschitz, right? Locally Lipschitz. So locally means, you see, as I told you, Lipschitz continuity is a non-local concept, or you can say global concept, right? It depends on the whole, whatever interval you are doing, you have to have the properties satisfied on the whole interval. Locally Lipschitz is the local version of that. So essentially you say that if, let's say, I am starting from AB to R, right? AB to R, AB to R, and you start with x naught, which is in open AB, right? Open AB. Then we say F is locally Lipschitz at x naught if there exists a delta greater than 0 such that F restricted to, okay, the ball with center x naught, okay, and radius delta is Lipschitz continuous, right? Lipschitz continuous. So essentially what I meant by this is, you see, at one point if you start with x naught, you need to have x naught minus epsilon and x naught plus epsilon. Let's say some interval should be there, which is of course contained in that in AB. Okay, so that interval, in that interval, if you restrict F, in that interval it should be Lipschitz continuous, right? Okay, so that is there. So this is the, I hope the concept is clear, right? So again, when it is Lipschitz continuous in whole AB is for all xy in AB, this property that fx minus fy should be controlled by some m times x minus y. Okay, now you see f is locally Lipschitz if for every x naught. So basically you start with an x naught, sorry, not for every x naught, or if you start with an x naught and you say it is locally Lipschitz at that point, if you have a neighborhood of such point where f is, when f restricted to that neighborhood is Lipschitz continuous, right? So it should not, it doesn't have to be Lipschitz continuous everywhere, but it has to be in a neighborhood. Okay, so for example, let's look at an example here. You see, fx equals to x square, if you look at in R, right? This is in R. Then we saw that f is not Lipschitz continuous. It is not Lipschitz continuous, right? Continuous. But you can see that let's say if you start with the x naught in R, okay, then you can of course choose a delta, then there exists a delta greater than 0. Okay, see any bounded interval. So essentially if you start with the x naught and you look at a, you can of course find a delta such that f, okay, restricted to b x naught delta which is x square restricted to b x naught delta. Okay, this function is of course Lipschitz because x square is Lipschitz continuous on any closed and bounded interval, right? So this is Lipschitz. So what does that gives you? It gives you that this is a function which is of course not Lipschitz continuous in R, but it is locally Lipschitz. So what we have gained here is the information is Lipschitz continuity is a much stronger condition. Locally Lipschitz is a much relaxed condition. Okay, and it is a bigger space than Lipschitz continuity. Okay, another small remark I want to add is this. See, let's say that if f is Lipschitz continuous, if f is Lipschitz in whatever Lipschitz, okay, in let's say whatever interval I is AB. Okay, it can be R also. I is AB. So let's say if f is Lipschitz continuous in I, which is AB, then f is uniformly continuous. This is very easy to check. Please do that. I want you to check this part, continuous. So please check. But okay, now the question which I want to pose here is this. Does uniform continuity of f imply Lipschitz continuity? Okay, and I will give you a hint. You think in terms of this sort of function, root over, let's say, the mod x, right? And x is in R. You think of it this way, or it doesn't have to be R. X is in some bounded interval, let's say 0, 1 or minus 1, 1, whatever it is. Minus 1, 1 or 0, 1, doesn't matter. Okay, so that sort of function. So think of the square root function and try to answer this question whether if f is uniformly continuous, whether this is a Lipschitz continuous function. Okay, and there is again another remark which I want to put here is this. Let's say f is continuous in a closed and bounded interval. Okay, so f is continuous in a closed and bounded interval, closed and bounded interval or bounded subset, doesn't matter, bounded subset of R, that will actually imply that f is uniformly continuous, okay, uniformly continuous in R, okay. So that is there. Okay, now that is more or less the whole idea of Lipschitz continuities. Yes. Now the thing is, let me just finish this lecture with a small remark, another small remark, but this is in a different context. Okay, so see, you see, if let's say I start with a let's say vector space which has some metric property. So basically you can think of it as this. Let's say that x to R, f is from x to R, and x is a metric space, Okay, now the thing is this: if I ask you that can you generalize the idea of Lipschitz continuity to this space? Can it be done? Okay, can one generalize the idea? Okay, generalize the idea of Lipschitz continuity, Lipschitz continuity. Okay, Lipschitz continuity. Actually, it can be done, and you can of course see that how you can do it. So please do it yourself, but I'm just giving you an idea. Once it is a metric space, okay, so once it is a metric space, this has a metric, right? So basically what you do is this: you see d of fx, okay, minus not minus, d of fx fy, that should be always dominated by m times distance of x and y. Okay, and since this is in R, you see this is in R, right? So basically this will actually can be written like this: f of x minus f of y less than equal m times distance between x and y. Okay, so you can generalize the concept like this. Of course, you can replace this x to another metric space y, and then this definition should work. Okay, but the thing is, what I want you to do is please check if it does or not. Okay, please check if the above idea works. Works or not. Clear? Okay. So with this, we are going to end this lecture.